All right, so kind of pick up where we left off with a little bit of housekeeping stuff before we jump into material. So if we go to Canvas page, kind of keep working off that week 5 do file, week 5 slides. Yeah, I mentioned last class that quiz and problem set. So the quiz, I'm going to keep the due date the same based on the material that's on that quiz. It was not anything that we talked about. There might not be any headers to assist stuff on there. So, you've had those practice problems or sample questions, I guess I call them. Start reviewing those. Kind of that quiz is due, the 18th. So before we meet in class on Tuesday. So as you're kind of going through those, if you have any questions, make sure you're reaching out to me to ask. I'll have kind of my normal office hours, hopefully, no unplanned surprises next week on Monday. So those would be a good time to come ask some last minute questions over those practice problems. Also, that problem set has been kind of out there. Because the last kind of stuff on the problem set is kind of related to what we talked about Tuesday, I figured I'd extend the due date a little bit. So instead of being due on Tuesday, let's do next Thursday. So you kind of have different due dates for those, giving you a little bit of buffer time in between. Once again, on that problem set, that also gives you opportunities not just to come by my office on Monday, but also on Wednesday for my other office hours, right? I just gave an exam in my other class, my big 251. So I probably won't have a lot of them showing up. So there'll be a good opportunity to kind of get in. You don't have to really fight any of them to kind of ask questions. A couple of you stopped by last Friday. Even though I don't have scheduled office hours, I kind of said I'd probably be around. I think that was helpful. Yeah, okay, a couple of I realize. So please use those. I want you guys to get as many points possible in those problem sets, and I'll try to help you quite a bit if you stop by. Okay. Other than that, any questions for me before we dive into material here? Okay. So we left off talking about this idea of when we run these regressions, what we're really doing is picking up kind of the difference between correlation and causation. Excuse me. So let me see if I have this before we can really dive into it here. Before I forget. All right, so today the topical happy Valentine's Day. I guess we're a day early. I used to suffer from omitted variable bias in my love life. I finally included it in my regression model. Now everything's statistically significant, right? So, right, we talked about if we leave out these important omitted variables, we sometimes can end up with these coefficients that aren't right. They're biased, right? They're baking in kind of the effect of these other variables that are going to impact Y that we haven't included. So we want to try to include them, right? We're going to talk about some of the issues that exist from just throwing everything onto that right side of the regression, but that's kind of what we want to do, okay? At least starting out, that's how we'll talk about it, right? So I've got this nasty slide that I pulled from some textbook I had to read in grad school. We're not going to go through this with a fine-tooth comb. This is the mathematical proof behind what the bias actually is being created. We're going to simplify it a little bit, okay? So if I had two variables that I think matter, right? So let's call this kind of x1 and x2, right? What's going to end up happening, so kind of write this out for us. We'll have a summary in the slides, but I think it's going to help kind of see me piece this together. So if I were to run a regression, and I include this variable that I think does impact Y, call it x1, right? Whatever it is. So maybe wages. I think the example I use is IQ later on today. Okay. Well, this will pick up the effect of IQ, but it's also going to pick up the effect of anything that's correlated both with IQ and wages. So something else that's correlated with both the Y and the X variable. So if I just run this regression, if we didn't have a bias, we would say, if I could run this regression and we kind of went through this thought experiment, and save those coefficients, and let's say I had 100,000, they should be normally distributed, and the expected value, or you can kind of think about it as the mean of those 100,000, whatever number I said, 1,000 coefficients, should be whatever that true population coefficient would be between that X and Y variable. Now, we only usually have one sample, sample data, so we're hoping that on average, our sample coefficient is what the true coefficient is. And that'll be true as long as we don't have important omitted variables. So if we have important omitted variables, when we run this regression, it will pick up what that true effect is between X and Y, X1, I guess I should say here, and Y. But it's also going to pick up the effect of the other important variable I left out. So if there's this other variable that I left out, and if I had included it in my regression, part of the estimate I see from Stata when I just run this simple linear regression, it's going to tell me the true effect of X1 on Y. It's also going to pick up part of the effect that's coming from this second omitted variable. Not only that, the size of what we're going to end up calling the bias in our estimate, right? How different is the predicted coefficient from the actual value will be related to the covariance or the relationship between the variable I included. So you can kind of think about, here was the variable that I included. Here was this variable I should have included, but I didn't, right? And then divided by whatever the variance is of that variable I included. Now, where that comes from was kind of that nasty couple slides, right? Why it ends up having that variance down there. We don't have to worry too much about that. We'll talk about kind of how it might play a role when we're thinking about different variables, but for us, this will be our bias, okay? So notice the size and sign of our bias will depend on, well, what's the covariance between the variable we included and excluded? That relationship could be positive or negative. Also, what is the effect of that excluded variable on our Y variable, right? So it's not quite perfect, but you can kind of think about this as like what the covariance would have been between Y and X2. In fact, if we go back, we said the coefficient, another way to calculate those is what? The covariance of those two variables divided by the variance. So if we had included it, that kind of would have been the coefficient we would have found. If it's easier just to think about, we're generally just going to care about the sign. So if we had included this second variable, what would its sign, what would it have a positive or negative effect on that Y variable? And then was the correlation or the covariance between that excluded and included variable, was that positive or negative? And we'll work through some examples where we say, okay, so our bias, we can put a sign to it. We can say it's going to be a positive bias or a negative bias. It can be one of those two, okay? Any questions on this here? So once again, this is the bias that exists if I don't include this important omitted variable. As soon as I include that important omitted variable, so let's say I run a regression, and we haven't talked about how we do this yet, but I can include, actually, yes, we did. I talked a little bit about last class in the R squared, right? So if I do include multiple variables on the right-hand side, what happens to this bias? Completely goes away. Right? So we don't have to worry about it anymore. If we have the variable, if we have the data, we should include it, right? We can eliminate that bias very quickly. But sometimes we don't have the data. And so we want to say, well, look, I know this other thing matters. I don't have data on it. So I know my regression results are a little bit skewed, right? And I want to know what that bias might be in those results. I shouldn't use the term skew because that has other connotations, but my results are biased, okay? So we'll kind of look at some examples of this, but this is kind of what we're going towards.
So when there's bias in our regression, does it show up in the R squared?
Yeah, so we'll hold off on the R squared discussion. But when we have this bias that exists, we're really going to be thinking about it's only in our estimates for the coefficient, right? The R squared will be influenced by the fact that we're omitting this variable, but in a very different way. We wouldn't call it bias. We'll call it some, I'll talk about in a slightly different way once we get to R squared later today. Okay. All right. So hopefully, based off problem set 1, do these look like things that we can calculate if we have the data? Covariances, variances, yes. All right. So let's take a look. Excuse me. What this looks like there. There we go. That's basically what I just had kind of written down on the dot can there. I wrote it a little bit more notationally correct, right? This is our covariance between X1, the variable we included, and X2, the variable we excluded, and then the variance is on the bottom there. Okay. Now, if we have a variable we left out and it's completely unrelated with the variables that we included. So let's say I'm trying to estimate the effect of IQ on wages, and I leave out the individual's height, right? I mean, what do you think the covariance is between height and IQ, right? The variable I included and excluded. there's some convoluted story you could probably tell me that they're somehow related, but right, we would think that covariance is probably 0. So what would the sign of our bias be? Well, if that covariance is 0, 0 times anything is 0. We don't have to worry about it. Also, if we exclude a variable, even if it's correlated with, so let's say I include, find a lot of examples of this one with my IQ example. Let's say I included, let's say I included my parents' IQ, right? So my parents' IQ, do you think that's likely correlated with my IQ? I don't know a lot about genetics, but yes, all right, there is some correlation there. But what's the effects of my parents' IQ on my job performance or my wages? Unless we're working alongside of each other, right? That effect of my parents' IQ on my wages should be 0, right? So even if we have an omitted variable that's correlated with the variable we included, as long as it's not correlated with y, we also don't care about it. It's only these variables that are omitted that are correlated with both y, our dependent variable, and the independent variable we included. Okay. Now, what does this guy look kind of like? Okay. So we talked about this, and I alluded to this a little bit, but if I run a regression, and let's say, actually here, we've got it up here, right? If I were to run this regression where I took that omitted variable, and I'm going to call this gamma, just so we have a slightly different notation here. If I did run a regression of that omitted variable on the variable I included in my regression, what did we say our coefficient estimates are? They're simply going to be the correlation between x and y. Well, here, y is x2. So that would be that covariance between x2 and x1. Just like we said, right? What's the coefficient? It's the covariance between y and there, divided by the variance of our independent variable. So what does this part of our bias actually look like? If we ran a regression where the dependent variable was the omitted variable, and we had this x1 variable that we included, that would actually tell us that second part of our bias as well. So we'll kind of take a look at this with some actual data, and I can kind of prove this to you, right? But we have a lot of the kind of similar things going on. A lot of this is representing just these coefficients of included and excluded variables, okay? So, oops, can't see the bottom there, okay? Does this hopefully looking a little bit familiar with what we talked about? I think I might have actually, on that problem set, I might actually ask you to calculate a sample coefficient without running a regression. How do you do that? Find the covariance between those two variables and divide it by the variance of your independent variable. Okay. So let's dive a little bit deeper into this. What do I have here? Well, I'll go through this before we jump to Stata real quick, but this isn't, I don't think, breaking news. I said that a lot of the questions I'm going to ask you, like if you think about the quiz, might just be not this current quiz, but the next one, right? The next one is covering this topic. Is maybe I just want to know the sign of that bias. So I have 4 different combinations, right? Because the effect of that excluded variable on y could be positive or negative. The correlation or covariance between my included and excluded variable or omitted variable could be positive or negative as well. Well, if I have a positive times a positive, well, what's the variance? The variance is always positive, right? So I really only care about the sign. Let me see, is this picking up my audio? Yes, okay. Of these two, right? So if I have a positive times a positive, my coefficient estimate I see when I leave out this important omitted variable will be 2 what? Well, if the bias is positive, my estimate is going to be 2. So if it's positive, I'm adding a value. So my estimate is going to be 2 high, right? If I have a negative times a positive, okay, well, now my bias is going to be negative. I'm subtracting a value. If I leave out this important omitted variable, what's going to be true about the coefficient estimate I see? It's going to be 2 low, right? And then the other combinations of those as well, right? Will give us kind of a sign. We could actually put a sign to that bias that say, even if we don't have this important omitted variable, we know which direction our coefficient is going to be off by, okay? Let's jump into doing some actual working data here. So we've got the MLR week 5 file. Make sure that's nothing. Okay. So I've got my global path here for class. I'm going to kind of look at this one right here. So we haven't really done this too much yet. I don't think I've done this for you. If I have, someone please correct me so I'm not just wasting time. Have I showed you how to use these free data sets? Don't think we've done this yet. I put these in here to try to remind myself. So you can use this command ssc install, and there's a bunch of free data sets that exist in Stata that you can just use. So you don't have to like have the actual file, go to file, open. This will open it for you. So I'm going to use some of these free data sets because they're free, right? So here, ssc install bqs, right? That kind of allows me to access all of these free data sets. So I can't see them behind the scenes, but it gives me access to them. So I'm going to go ahead and run that code. I'm then going to just clear out. That's just in case I already had a data set open. That clear command just empties out my data set so I can open up a new one. Okay. So when we were opening things up like manually, like go to file, open, a lot of the times it'll throw in that clear command at the end. But for us, we're going to have to clear everything out if we want to use these free data sets. Okay. So I'm going to clear things out, and then I'm going to put, okay, I can now use this bqs because I've installed it. And I don't know if this might take, has anyone run this yet? Is it taking a little bit of time? No? Okay, so you'll kind of notice it tells you like, checked it, verified, everything's up to date. So I'm going to run these 2 lines. Oh, just open a data set. It lets me know what all these variables are. And here they are now opened up in my data set. Now, I'll walk you through these. I won't ever just give you one because a lot of the times it's not quite clear unless you have some knowledge. You can like Google search these data sets in Stata and find out exactly what KWW means. I believe that's knowledge of the working world. It's some test that they give to these students in this data set. So, you know, the variable names usually help us out, but sometimes it's not quite clear. I won't ever try to give you anything where it's not clear, right? So we're now going to use this data set. We'll skip over this because I'm going to kind of do things a little bit different order. We'll come back to dummy variables in multiple linear regression. So we opened up that BQs data. That was one thing I wanted to kind of show you. We have multiple data sets we can use, so not just wage. I'm going to go down here. Now notice if I don't clear it out and I try to use another data set, call it GPA2. Oh, actually, it did clear this out for me. I thought you had to add in the extra clear command to kind of wipe out the previous data. Maybe they updated that in the newer version. But to be safe, always kind of clearing it out will make sure you're getting rid of that old data, opening up the new one. Okay. So we'll kind of use this college GPA and this athlete variable example. So if I run a regression of college GPA, and then I've got a dummy variable for whether or not the individual is a student athlete. Okay. So how would I interpret this slope coefficient? So what's a 1 unit change in my X variable here? If it's a dummy variable, if the student is a 1 or a student athlete relative to the 0 group, so if they're an athlete relative to a non-student athlete, the predicted change in, well, what's my Y variable, GPA in college would go down by 0.28 points, right? You know, tell the stories of time commitments, things like that. But also, what do you think? Let's make sure yeah, I thought so. You know, what do you think is probably true? Not to be stereotypical, but what do you think is probably true about the men's football and basketball teams' admission standards relative to you? Do you think they're higher or lower? Lower, right? So even though I run this regression, maybe it's not that being a student athlete is having a negative impact on the GPA, right? In fact, being a student athlete teaches you time management, right? And forces you almost to be a little bit better at time management, and actually could have a positive impact, right? It connects you with people, right? That, you know, juniors, seniors that might kind of have some advice, things like that. So maybe it's not that it's this huge negative impact on your GPA. What could this be picking up the effect of? That student athletes are on average, I wouldn't say it dumber, but right, they might have lower admission standards, right? And that their raw ability in terms of intellectual ability might be a little bit lower because their standard, admission standards are lower. So we'll take a look at this, right? So if I was thinking about what bias would exist here, I'll kind of write this out. I just ran a regression where I had college GPA and whether or not they were a student athlete. So the estimate I just found was like negative 0.28 or whatever it was. It probably picks up the true effect of being a student athlete, but it's also going to have this bias component. What was the bias? It would have been the effect that if I had included something like, let's use their SAT score as a measure of what their kind of intellectual ability was before college. What would that effect have been on my GPA, college GPA? I should be clear here, college GPAs. Multiply by the covariance between what? My included variable and my excluded variable divided by the variance of, and here, it's harder to remember this one, it's the included variable. So what do you think the relationship between SAT scores, higher SAT scores are with college GPAs? Positive, right? I don't think that's not breaking any news or making a hot topic here. What's the covariance likely of being a student athlete? And I believe these were all like large D1 universities and SAT scores. It's likely that student athletes relative to non-student athletes, their SAT scores are going to be a little bit lower, right? Their admission standards are lower. So what's the sign of my bias here? Positive times a negative. What is my variance? My variance is always positive, right? Variances are always, so my bias would be, positive times a negative over positive would be negative. I'm thinking of another example I have, okay? So the estimate I see of negative 0.28, that's going to be too low, right? It's going to be a larger negative value than what the true effect likely is of being a student athlete. So we can actually see if this is true with the data, because I actually have SAT scores in the data set. Is this, any questions on this before we keep moving? Yeah, I don't think this is not terrible yet. So we've got our naive coefficient. I sometimes will say that, like, if we omit this important a variable, here's the naive coefficient. We know it has a bias in it, right? Let's see what that bias actually is. Well, let's run a regression where I actually include the SAT variable. As soon as I include it, what happens to my bias? I said it does what? As soon as I include that important omitted variable, my bias goes away, right? Completely eliminated because I'm now including it. It's no longer omitted. So if I run this regression, sure enough, now once I control, remember, how do we interpret these multiple linear regression coefficients? It's still the same interpretation. Being a student athlete relative to a non-student athlete, the predicted change in GPA is now that it would be 0.05 lower. But what do I get to add on to the end? Holding constant the other variables I included. So holding constant the SAT score. So now the thought experiment is two students with the same SAT score, but one of them's a student athlete, one of them's not. The student athlete, we would predict their GPAs a little bit lower here, 0.05 points. And maybe that's because, time commitments, things like that. Any questions on this before we keep moving? So before we talk about, well, if I do have the variable, what was the size of my bias here? So before, I found an estimate of negative 0.28. Now, once I include the omitted variable, the estimate is what? Negative 0.05. So the bias was approximately what? Negative 0.23, if I'm doing math in my head correct there, right? So we can just look at, if we have the data, we can see, run a regression with and without this variable, what was the difference that was created. That's our bias. Now, if I didn't have this SAT score variable, maybe I don't know, or I had a different data set that had SAT in it, and I want to understand, well, what would the size of this bias look like if I could include it? we can do that as well. So, excuse me, I'm going to run this command where I'm just looking for the covariance between athlete and SAT score. Okay. So I now have the covariance between athlete and SAT score. These cross ones, these also represent the variant. We could use the sum command, but these also represent our variances. So remember, we said the bias is going to be the effect of what the omitted variable would have been on y times the covariance between the included and excluded variable divided by the variance of the included variable. Right? So we now have the covariance of the included and excluded variable. We have the variance of the included variable. Well, I can kind of cheat here because I also know if I had included SAT, what would that coefficient have been? 0.0019. Now it's just a matter of plugging everything into my equation, right? So I think I have it in the comments here, right? You would take what that beta 2 value was, multiply that by should be that, right? Sorry. Am I looking at this right? Yeah. So that's my beta 2 value. Here's my covariance, and I'm dividing that by my variance. Okay. So that should give me that value of negative 0.23. You can prove this to yourself. I guess we could, I don't know. Access Excel real quick. All right, we could take that. Okay. Well, right? I get that bias of negative 0.23 without even having to run that second regression, right? Just using the covariance and the variance of those variables, okay? So all I was doing there, just to be clear, I had beta 2, was like, what was it, 0.0019, right? I then had the covariance, it's like negative 5.4 something, and I had the variance on athlete, which was like 0.44 or something like that. So I'm just plugging it in and figuring out what that bias value was. So two different ways, really, of showing that the bias, if I run that naive regression, the estimate shouldn't have been negative 0.28. It should have only been negative 0.05. Okay, that's quite a bit lower, right? So, I mean, we're talking like percentages, right? That's what, I don't know, 80% lower. So approximately, I'm doing some really rough estimates there. Okay. Any questions on that idea? Okay. Now, I also said, if I have the data, I can run the regression where I include it and just see, oh yeah, sure enough, the difference between those two coefficient estimates was negative 0.23. And that'll always be the case. Okay. I think also there is some discrepancy here. It's because I have to round somewhere, right? So they're you know, out to the fourth decimal, they might look a little bit different. If I ever ask you for this on a problem set or a quiz, right, I'll either have on the quiz like the margin of error wide enough to accept the rounding, or on the problem set, right, I can go, you know, I'm going through them. I can see that you did the right method, right? It's just a rounding issue. Also, I have my, just to remember, I have that my TA helped me grade those first problem sets. I think I mentioned this. So you might start seeing some comments pop up as they work through those. You know, these first one or two kind of, it might take a little bit longer for them to kind of get through it. Once they get the hang of it, they should get back to you a little bit quicker. Okay. Any other questions before we keep moving here? So let me make sure. Yeah, this was the example I had in the slides. So we kind of went through all this, but there's some summary of the output that we would see in Stata. We just kind of worked through it all. I want to do one more though before we move to the R squared, because I did mention this, right? So we have this alternative method, which I said, what does that second part of the bias actually represent? So we said, this portion of the bias looks something like, oh, if I were to run a regression of where the omitted variable was my dependent variable, my independent variable was this variable I included, that coefficient estimate would actually be that portion of the bias. So we're going to try to kind of prove it this way as well. Okay. So first of all, we already found. All right. So what are we really looking for? We want to know what this bias is. We already know because we ran the regression, this was what, 0.0019. To find this second part, I'm just going to run that regression where we had what? SAT score was our omitted variable. And I want to find the coefficient estimate between that and our included variable, X1, which was student athlete. Okay. So if I run this regression, this gamma 1, that is this second part. Okay. So hopefully I'm going to prove this to you. So if we go back here, I'm going to run this regression where I'm looking at college GPA, student athlete. So this was my kind of naive regression. Yeah. Oh, thank you. Sometimes I don't hit this hard enough. So this was my naive regression, right? I know that estimate's too high. If I run the regression where I include SAT, we said we can figure out what the effect of SAT score should have been on my college GPA, or what beta 2 was. Now, the other thing that we needed was that second part of the bias, which we said, well, I could calculate the covariance and the variance and do it that way. Or if I run a regression where the dependent variable is that omitted variable of SAT, and then I use the included independent variable student athlete, the coefficient, the slope coefficient there should be that second part. I should only need one value now to plug in there. So if I go ahead and do that, I get negative 122. Well, what do you think if I take negative 5.46 and divide it by 0.45? That should be negative 122. So if I take that value now, multiply it by beta 2, I end up with that same value of approximately negative 0.23. Right? Once again, some rounding issues there. We have to round somewhere. Okay. But that's another way of kind of showing what the size and the sign of that bias are. Any questions on anything there? You'll see something again.
Yeah, so, like a definition of a bias be like how much of an effect that beta 2 has on beta 1, that kind of what it is, or is it?
It's really two components, right? So if you want to break it down this way, the bias that exists is being partially created by the effect that that variable, omitted variable, would have had on Y. But it also, how much that bias would be, depends on what that omitted variable's relationship was to the variable that you are actually interested in the coefficient of, right? We're interested in the coefficient of student athlete. So yes, we know that the SAT score variable will likely have a positive correlation with our SAT, but if it's not correlated at all with being a student athlete, it won't cause a bias. Part of that bias comes from the fact that this omitted variable, not only is it going to have an impact on our dependent variable of Y or on college GPAs, but also it has to be that it's correlated with that variable we included. That SAT scores are correlated with student athletes. So let's say I had a different data set. Let's say I ran this for, I don't know, like community college. Yeah, it's community colleges, right? What do you think is likely true about their standards for student athletes versus non-student athletes? Pretty similar, right? So there, what would my bias be if I ran the same regression? Well, it's likely that being a student athlete isn't correlated with SAT scores, so that bias would be pretty close to 0, right? So it's two parts that matter. It's correlation with the Y dependent variable and that omitted variable's correlation with the variable that you included or that you're interested in the coefficient of.
Okay, so the fact that SAT scores matter in this case, it's why.
That is part of it as well, right? If that omitted variable doesn't impact Y at all, it doesn't really matter that we're omitting it. Yep. That's the idea if I left out height here. I'm sure height is a great example, right? So if I think about, I'm probably going a little bit further, but that's a good question. So let's think about if I ran this regression where I wanted to know GPA, student athlete, And the variable that I omitted was their height. And let's think about basketball specifically, right? Well, the coefficient estimate I see if I omit that variable of height will be the true effect of being a student athlete on GPAs, plus what would the effect have been if I included height, times the covariance between this omitted variable and the variable I included, right, my independent variable, divided by the variance of the variable I included. Well, here, why does it not matter that I left out height? I am almost positive this covariance is large and positive, right? Your height is probably increasing your chances of being a student athlete, especially if we specify being a basketball player, right, at IU, right? But what is the effect if you include height on GPAs? Once again, there might be some convoluted story, but this is probably going to be 0. So there, I won't really have a bias either if I'm omitting variables that aren't related at all to my dependent variable. So it has to be both. Is that, yeah. It's good questions. I should have thought of using this example earlier anyways, right? So any other questions on that before we keep moving here? Okay. So once again, we kind of went through all this in Stata. You've kind of got some summaries of this in the slides. We don't need to walk through this. The next thing that I want to kind of transition to talking to with multiple linear regression is when we start adding in, so we know these omitted variables exist, right? And don't feel like you have to write this down, but just to kind of prove the point here. I think best. So not only will a bias exist if we omit this important variable, but what if we omit another important variable? It would be the effect of that variable times the covariance of that variable with the variable included, plus what if there's another variable? So we could have multiple biases baked into that coefficient, right? So how can I eliminate all those biases? If I have data, if I have those variables in my data set, I can just include them, right? As soon as I include those omitted variables, all of these biases are eliminated, okay? So if I think about what impact is that going to have on my R squared? If I am thinking about my R squared, the technical way we study this is it's the proportion, of the variation that we can explain using our predictions. So if we were going through every single observation, come up with these predicted Y values, we said we would look at, okay, what's the deviation of that prediction from the average? That's the amount of variation the variables that we included on that right-hand side would explain. What would the denominator of our R squared be, this total sum of squares? Well, it's the deviation of the actual Y values from the mean. So this is going to represent the total variation that exists in Y. So if I take how much variation I can explain, divided by the total variation, this is going to represent the proportion of variation I can explain. And if we want to kind of go back and forth, a lot of the times we'll talk about R squared as a percentage. My R squared is 0.25. That would be how much am I explaining as a percent? 25%. Okay. So as I include more variables, what's going to happen to my R squared? If I try to use more variables to predict something, I can explain what a higher or lower proportion of it. Hopefully higher. At the very worst, what's going to happen to my R squared? It's going to stay the same if I include height or something that doesn't matter, right? So, you know, kind of looking at this with our previous two examples, just to kind of have the Stata output here. Initially, when I just used student athlete, my R squared is like 0.008. So I'm explaining 0.8% of the variation that exists in college GPAs with just if someone's a student athlete. Looks like that doesn't matter a whole lot, right? Now, if I include SAT, do you think that is going to be a good or bad predictor of college GPAs? There's arguments that, like, I don't know, SAT's bias, all this stuff. But based on our data, it increased our R squared to about 16%. So it's a pretty good chunk, right, of the variation that exists in college GPAs can be explained with SAT scores, which is why admissions departments ask you for your SAT scores, right? Because it's predicting what your performance will be in college, right? That's what they're doing. Right? There are equations, like they are running these regressions behind the scenes. There's a reason why they want to collect that data from you, because they can predict what your success will be once you get here. So I'm digressing a little bit into issues that hopefully you can kind of connect with a little bit. But as we include more variables, our R squared is going to go up. Okay. So how much higher is it going to be? Well, we think about here, how much additional variation did SAT scores explain? Well, we went from what, 0.008 to 0.167. So really just under 16% more variation, right? Think if I, what, 0.167 minus 0.008, right? Like 0.159. Okay, so 15.9% more. Okay. Now, another statistic that we have here in our regression output is this adjusted R squared. So if I wanted to, do you think I want a higher or lower R squared? Higher. That's telling me I can explain more of the variation and why the thing I'm trying to predict. So my predictions would be better, right? Now, if I just start throwing every variable I have in my data set at this, we'll talk about some more issues that would exist. But as I just start throwing more things at a regression, put more variables in that right-hand side, I always know that my R squared is going to go up. This has to, right? So you can kind of think about maybe what I'm more interested in is like, what's my per variable explanation of this Y variable, right? I know I could throw 100 variables on the right-hand side and get an R squared really, really high, right? But it also required me to use 100 variables, right? Now, we won't really dive too much into the theory behind why, but as I use more variables, it kind of cheapens my data set, right? So if I have a small data set, like with a sample size of 50, if I start to include like 20 or 30 variables, the problem is there's not a lot of variation in my data set now, right? Let's say I had 50 observations and I include like 50 variables. It might be that every single person has a unique combination of those. I can't pick up any variation. So when we add in more of these independent variables or right-hand side variables, it's going to cause some issues with our R squared measure, right? We know it's going to inflate it, right? And it's actually going to inflate it a little bit too high, okay? So our adjusted R squared will try to account for that. So if you look at both of these, right, this one's just barely smaller, but our adjusted R squared will always be less than the R squared, right? And what we're going to do is we're going to adjust that R squared for the fact that we were including more variables, okay? So how are we going to do that? Oops, let me get this out of here. So usually what we would do, I explain the R squared usually this way. It's how much of the variation can we explain divided by the total variation that exists in Y. Another way of saying that is what amount of variation can I not explain divided by the total amount of variation. So this would represent the proportion that I can't explain. Well, if I subtract that from 1 would represent, remember, R squared is a proportion. So if I had an R squared of 1, what percent of the variation am I explaining? 100%. So if I take the proportion I can't explain, subtract it from 1, that should give me the proportion I can explain. Now, the reason why I'm rewriting it this way is not just to be a jerk, right? The reason why is because when we adjust our R squared, we're actually going to adjust this proportion of variation that we can't explain by this factor, right? So this factor that we're using to adjust is going to be n minus 1 over n minus k minus 1, where k just represents the number of independent variables or right-hand side variables or x variables that we've included. Okay? So like in our previous one, we only included 2, right? Athlete and SAT, so our k would be 2. So we'll think about the things that are going to impact this adjusted R squared. Excuse me. So let me think, make sure I didn't miss anything here. I didn't. So good. I sometimes give myself notes just to make sure. So one thing I already said was our R squared will always be less than, and I will likely always use the subscript here. If you look like in the textbook or something, the adjusted R squared is usually the notation used is putting a bar above it. I don't know. I don't really want notation to be like a huge hindrance in this class. So when I'm writing things out, I will likely kind of say, I'll also throw in like this adjusted next to it, right, as a subscript, just to identify like this is our adjusted R squared. Okay. So we know that it's always going to be a little bit lower because it accounts for the fact that we've included more variables on the right-hand side. So if I think about this adjusted R squared, and I said it was 1 minus RSS here, which really I'll kind of identify where you can find this in the state output. This is the residual sum of squares. So I said, what's another word for kind of residual? Or what is residual another word for? Error, right? So error, residual, statistics, they're kind of the same thing. So this is like how much is in the error term that we couldn't explain divided by the total amount of variation, right? So the variation we couldn't explain divided by the variation we can. And so total variation, unexplained variation. And then we multiply this by this factor of n minus 1 over n minus k minus 1. So let's think about what's going to push my adjusted R squared further away from that R squared value, okay? So the first thing we'll think about is, because we've talked about it, what happens if I just start to include, and actually here I'll use red, right? I wrote the same thing, but I'm just going to color code it, okay? If I include more variables on my right-hand side, what's going to happen to the gap in between that adjusted and my R squared and my adjusted R squared? So let's assume that we were able to explain the same amount of variation. So we're not kind of thinking about how it's impacting this, and in fact, we won't ever dive into that. But how is it kind of influencing this scaling factor? Well, if k goes up, what's going to happen to my denominator? I'm subtracting a larger value. It's going to go down. My denominator here is smaller. What's happening to this fraction? It's getting higher. If I'm subtracting a larger value, what's happening to my adjusted R squared? It's driving it even lower, right? So the gap in between my R squared and my adjusted R squared, if I'm finding the same kind of values, but from including more variables, that adjusted R squared is going to be even further away from that R squared value I see, right? It's going to be an even larger adjustment, and that's because you didn't just include 2 or 3 variables on the right-hand side, you included 50, right? Of course, you're going to get a higher R squared. So that adjustment factor would kind of push that adjusted R squared a little bit lower, right? Or if you want to think about the gap in between the actual and adjusted R squared is going to actually go up, right? It's going to get larger. Now, what's another thing that, really the only other thing here that could change? What if I take, excuse me, larger sample sizes? So if I take larger sample sizes, this one's a little tricky. What does this fraction always have to be less than? N minus 1 over n minus k minus 1. What's the lowest k could be if we run a regression? We only have one variable. In that case, what would be true about that fraction? So let's think about, if I had n was 2. Well, not 2. Let's do 5. 5 minus 1, 5 minus 2, right? So I'd have what? 4 over 3. This is always going to be something that's above 1, right? I'm subtracting an additional thing in my denominator. That fraction has to be kind of greater than 1. So as I increase n, what's going to happen? So I just used the thought experiment if we had n of 5, right? And we said that would be, and I only had one independent variable. That's the easiest one to think about. So let's do that. Just write that out, right? So 5 should be 4/3, right? Or what? 1.33 repeated would be this guy. What happens if I had something like 555 observations? This is going to be what? 554 over 553. What is this really close to? So as I increase my sample size, what's happening to this fraction? It's getting closer and closer to 1, or it's going down. Right? So sample size goes up, and I'll kind of write it down here. What's happening to this fraction? It's going down. If I'm subtracting a smaller value, what's happening to my adjusted R squared? 1 minus a smaller value would be if I subtract a smaller value from something, it will be larger or bigger, right? So as I take higher sample sizes, what's happening between the gap from my R squared and adjusted R squared? Well, my adjusted R squared is going up. It's actually getting closer to that actual R squared value I'll see. So my gap is going to go down. So when we add in more variables to our regression, it'll widen the gap in between that R squared value we see in our adjusted R squared. If we were to take larger sample sizes, it has the opposite effect. So what's a combination of these two things I can do to kind of ensure that my R squared value and my adjusted R squared are pretty close? Because in practice, well, maybe there are 50 omitted variables I think all matter. Well, if I include all 50, I know I'm going to be driving my adjusted R squared closer and closer to what value? It just keeps going lower. It's getting closer and closer to 0, right? Well, that would mean I can't explain anything. But if I want to include all 50 variables, what can I go ahead and try to do? Get really large sample sizes, right? I know that's going to have the opposite effect. So even if I want to include a lot of variables on that right-hand side to try to predict why, one way I can do that is get really large data sets, right? And that way I know that kind of my R squared value is going to be closer and closer to that. Oh, come on. Adjusted R squared value, okay? Is this making sense what I'm saying here? Any questions over anything? Okay. Yeah.
So when you just have one predictor for your model, would R squared adjusted be better than R squared? Or
Would R squared adjusted? The adjusted R squared. So here's the what really the problem is. If I'm comparing across different types of relationships, or I'm like saying how much variation does this variable explain? If I try to compare the R squared of a regression that has 2 right-hand side or independent variables to a regression that has 50, I can't really just compare those two using the R squared. Now, what I can do is say which one of these regressions is better. I can compare their adjusted R squared because the adjusted R squared accounts for the fact that if I have, like, let's say the relationship between GPAs and being a student athlete and then wages and IQ. Well, and let's say I had wages, IQ, average income in the county, parents' income, all these other variables, I now can compare across those two if I'm using my adjusted R squared. Because the adjusted R squared accounts for the number of variables used in each regression, right? If I'm kind of computing them individually, and it also accounts for the fact that there might be different sample sizes in those two data sets. So I'll show you here. It's a good question. So let me, oops, there we go. Oh, do I have one here? Well, this kind of makes the point. This will make the point about our larger sample size, and then I'll kind of come back to your question because it's a good one. So let's say I had this regression where I've got 2 independent variables. So K would be 2, N is 4,000 something, and I get this R squared of 0.1673. Well, sure enough, when I have a really large sample size, we said that gap in between my R squared and adjusted R squared will be pretty small, very small, right? They're almost the same value. But now if I want to compare this and say, okay, is this a better, am I making better predictions about college GPAs here than the predictions I'm making about wages using just the 2 variables of IQ and the individual's race, right? So I don't know if we'll quite have enough time to talk about this today, but it'll lead us into talking about dummy variables. So this is going to be my next example. I think we'll probably, we'll have time to go through it today. Well, notice here, the sample size is smaller. So what's happening, that gap, it's not much wider, right? Right, this is like, what, 0.0005 4 is the difference. With a smaller sample size, that gap should be wider. Sure enough, it's like 0.00, approximately 2. Right, so that gap, and it's not much, there's just still a small difference, but it is a little bit wider. Right? Now I can use the adjusted R-squared to compare these regression results to the other ones, because my adjusted R-squared accounts for my sample size differences. And if I had, say, included 4 or 5 more variables here, it would also account for that. But really, yeah, the usefulness of the adjusted R-squared is to be able to compare different types of relationships across different data sets. Does that make sense?
Yeah, thank you.
All right, so this leads us into final topic I want to go through, but make sure before we get there, because we've still got what, 20 minutes? Yeah, we're good. Let me see if there's anything else I had in here. I don't think there was. Yeah, this jumps to kind of dummy variable stuff. I don't think there's anything. Let me see if I have something up here that would be useful. Dun, dun, dun. Yeah, we should be good. So we've talked about omitted variable bias. I'm going to come down here in the second regression I had. Okay. So once again, I think this is the one I skipped at the very beginning of the do file. It was another one of these free data sets. It's a bunch of wage data, and it's got a bunch of information for individuals. If we have time, we might play around a little bit and do some stuff that's not in the slides. That might be worthwhile to see. So what I've got here is I'm trying to predict wages from an individual's IQ. Right? And then this data set had dummy variable identifiers for the race that the individual identified as. Right? So we're just going to use one of those racial groups, and I'll kind of show you the power of what we can do with regression, some of the social statements we might be able to make. Right? So let's say I run this regression, right? And I'm thinking about, I'm going to try to kind of give a visual. And what I'm interested in is this maybe relationship between IQ and wages. Okay? So let's for a second think, if this is a dummy variable, right? Indicator variable, 1 if the individual identifies as Black, 0 if not. What would the predicted wage for an individual who doesn't identify as Black start out as? So if their IQ was 0 and they are not identifying as Black, their wage would start out as, well, the only thing left in our regression would be beta 0. Now, technically, right, when we run this regression, these are all estimates, right? But this is where their wage would start out. As IQ goes up, what do you think is probably true about beta 1? Higher IQs, do you think those are resulting in higher or lower wages? Probably higher. Hopefully, I mean, if it's not, I don't have an explanation, right? So any data set I've ever seen, this is a positive coefficient, right? So it's likely that if we were to graph out this relationship, and let's say, right, we had something like this. So we're predicting that y variable. What's the slope? The slope is the estimate we have for beta 1. Now, all these black dots here, these would kind of represent just the observations of individuals here who belong to the 0 group. Right? So this tells me about predicted wages for individuals and they're, for various IQs when they're non-Black. Right? Now, let's say I think about making predictions for individuals who are Black. Right? Let's assume, and this data set's old, I think when we look at the actual values, this is hold true. This was like older, like 80s data, if I remember right. What do you think is probably true about discrimination in the 80s relative to even today? Do you think it was better or worse? If you guys have taken a history class, generally we're working in the right direction, right? We still have issues, but we're a lot better than we used to be, right? So it's likely that I would expect right, what would the interpretation of beta 2 be here? For an individual in our data set who's Black, belongs to that coded 1 group, relative to the 0 non-Black group, what is the predicted change in their wages holding constant their IQ? So the thought experiment is I have 2 individuals have the exact same intellectual ability. what do you think's true about the individual who's Black's predicted wages if we have discrimination going on? They're going to be lower, right? We have discrimination. So what's going to be true about their intercept? If I try to make a prediction for someone in this data set who identifies as Black, it starts out at an IQ of 0. It would start out at beta 0 plus beta 2. Well, if there's discrimination going on and the effect on wages of being Black is negative, it could be that their predicted wages are lower, right? In fact, maybe, this is kind of weird, so this is where sometimes our intercept interpretations get weird. Maybe this is all the way down here. Well, and you're like, well, how can you have negative wages? Well, that's because we never have someone with 0 IQ, right? So these intercepts get kind of weird sometimes, but maybe it pushes the predicted wages, the starting point for this one group, this other kind of this whatever racial group we're looking at. If there's discrimination going on, it would predict that they start out at a much lower intercept. Now, here, what's the effect as their IQ goes up on their wages? Well, we would still get that same predicted relationship between wages and IQ. It's just that they're starting out at a lower value because of that effect of that indicator variable, right? So if we were to take just the observations in our data set and do a scatter plot, well, we can't have negative wages, but right? Something like this. It's almost like when you include a dummy variable, what does it look like we're estimating? 2 lines of best fit. It's almost like we're taking the data, pulling it out into 2 scatter plots and estimating a line of best fit for both. Now, we're assuming the effective IQ on wages here is the same across both groups, right? But we're allowing for that starting point to differ, right? So when you include these dummy variables or these indicator variables, we're going to have essentially like shifts in the predictions for that one group. Now here, like I said, if I was doing wage data, a lot of times, unfortunately, what we find is that that beta 2 value is negative, right? It actually predicts that individuals in different racial categories start out at a lower value. So once again, not saying this is true. I mean, well, probably is true right now, but this data set's a little bit older. So hopefully it's gotten better than what we see here, because holding constant someone's IQ, the predicted wages of these individuals just from simply being identified as Black, $129 lower, right? And once again, I can't remember those weekly wages or something like that, but right, it's a pretty significant effect. In fact, here, could I say that holding constant IQ, that an individual being Black here actually has a statistically significant effect on their wages? I look at that indicator variable, this p-value is basically 0. We started assuming there is no effect. I can reject that. I found strong evidence here. Essentially, there's statistically significant evidence at any one of our benchmark kind of levels, we've got discrimination going on, right? So, you can do this with whatever you want, gender, well, maybe. I actually have a data set. I did this once thinking about like how different majors are treated within the college. So like econ majors are treated very differently than Kelly school majors, things like that. But yeah, this allows us to kind of identify things that might be going on. And it's pretty powerful. Like here, it's just one variable, right? So maybe I'm thinking about what could exist in this coefficient that we talked about most of the class today. Our estimate could be bias. We could have a bunch of omitted variables still, right? I only have 2 variables to try to predict wages. Now, as I start to include more and more variables, if I still see that this is negative and statistically significant, that's really powerful. So if I look at this data set that I was using, so we scroll all the way up, was that free one, which was wages. So let's say I start to include, I don't know, I have that same regression. Oh. So I copy this. And let's see, what are some of the other variables? I've got like mother education, father education. Are they in an urban area? Is it in the South? Are they married? Age, experience, tenure? Right? I just start throwing the kitchen sink at this, right? All the variables I can include. Well, this interpretation was holding constant the person's IQ. What was the impact being Black in their wages, right? That would be some evidence of discrimination. Now, what is the interpretation of that coefficient on the Black identifier variable? 2 individuals with the same IQ, their mother and father had the same years of education, They both are from either an urban area or they're not. They're both either from the south region of the country or not. They're both married or not. They have the same age, same experience, same tenure at their job. Now what's the effect on their wages of being Black? Well, hopefully a lot of these omitted variables, hopefully that drives that coefficient estimate closer to what? I mean, we don't want discrimination. So hopefully that coefficient gets closer to 0, right? So sure enough, we kind of throw the kitchen sink at this. Okay, it is going down, right? It's not negative 129 anymore. It's negative 55, which is still negative, not good. However, now, can I actually say at any statistically significant level that there is evidence of discrimination from this data set? So what's my p-value? 0.28. So when can so what do I always start out assuming? The coefficient is equal to 0, there's no effect. At any of my conventional levels where alpha is 0.1, 0.05, or 0.01, 90, 95, 99% level, can I reject at any of those levels? My p-value is not less than any of those alphas. So I would say I have no statistically significant evidence that actually, once I can control for all these other factors, that I do have evidence of discrimination in this data set. Okay. So you can see as we include more variables, these interpretations of our coefficients become way more powerful. So we're holding way more things constant. Also, what am I doing as I include more of these variables? In all of my coefficient estimates, I'm eliminating a lot of that omitted variable bias. Now, just a word of a little caveat on all this. And I think I've got, let's see how far, I think I jumped down. I think it's at the end of this. Yeah, we'll probably talk about it next week. Because I've got another example where I think there's some interesting stuff going on with discrimination. We can look at like gender and race stuff. Even though we found no statistically significant evidence here at our conventional levels, what level could I say there is evidence at in terms of what confidence could I say I found that there was some discrimination going on? Yeah, right. 70% confidence would mean a significance level of 30%. In decimal form, that's our alpha. So 0.3, that p-value is less than 0.3. So even here, I could say I found evidence of discrimination with 70% confidence. That's not nothing, right? That isn't, doesn't meet our usual kind of benchmarks when we look at like academic papers, but it's not no evidence, right? So we want to be careful thinking when we talk about statistically significant evidence, like, yeah, just because it doesn't make our usual threshold cutoffs, like it's still a piece of the story, right? It's still something that probably shouldn't be completely ignored here because it's not like it's a p-value of 0.82 or something like that. If you're looking here, what is like strongly predictive of wages? So that would be things that statistically significant, they would have p-values close to what? 0. So it looks like here what? IQ, not surprising. The married one shocks me a little bit. That's interesting. Maybe you have your life together a little bit more. You might have someone that actually you have to provide for, so maybe that's what it is. Age, right? Is also, and then whether or not you're in an urban area, that makes sense. We know the cost of living is higher in cities relative to, in Indianapolis relative to Bloomington, and so you have to pay workers higher wages. Some of these things don't look like they matter a whole lot at all. The one that's surprising is going to be his experience variable. Actually, something kind of weird going on with that, which we should be able to talk about next Tuesday. So up to this point, we've talked about bias that exists in our coefficient estimates, right? Just these coefficient estimates. We'll talk about some issues that exist when we run these regressions related to what we call collinearity. And this experience variable is going to fall victim to one of those, right? So that's a little bit of foreshadowing. Up to this point, we've just talked about the bias that exists in kind of these coefficient estimates. Point out one more thing kind of with this example as well. So even though we're talking about the bias that exists, if I go back and run this basic regression without as many controls. So notice the coefficient estimate can change in size. Well, how do I calculate my test statistic for these coefficient estimates? So this is, once again, this class builds on itself. But I calculate that test statistic by simply taking the estimate for that coefficient and dividing it by what? Thank you. So we said there's another column in our state output. For every variable, we have a coefficient and we have a standard error, right? We said we can think of this as like kind of like the standard deviation of these coefficients. So if this made my coefficient smaller, what's happening to my test statistic? It's also getting smaller. So what's going to happen to the area to the right of it? It's going to become larger. So my p-value is going to go up. Is it going to be more or less likely I can reject the null? Well, if my p-value is higher, I only reject when the p-value is less than alpha. So if my p-value is higher, it's going to be more or less likely I reject, less likely. So not only is the fact that we have this omitted variable bias going to cause issues with our coefficient estimates, but because it impacts those, inherently, it's going to impact our rejection decisions, possibly leading us to make rejection decisions before when we had omitted variables that we actually shouldn't have been making. Did you have a question? You sure? Okay. All right. So other than that, we've got a couple minutes left here. This should be easy. I'll reward you guys for showing up here. Let me change this real quick, just in case. Give some buffer time so that making sure if you're getting out of here, there's no kind of issues, right? So it should just be 2 questions that we've covered today. Once again, I'll kind of walk us through these. So they should show up on Canvas here. Go to build. And there might be some weird things with the initial scoring. I'll get updated. Just to kind of think about the types of questions and kind of give you some stuff you can think about. So let's say I was running this regression where I had college GPA and whether or not someone was working a job, right? So this is a dummy variable, 1 if they're working, 0 if not. If I had an important omitted variable of parental income, what would be the sign of the bias? So if I have this omitted variable of parental income, what is that bias composed of? We said to find out the sign, we need to know what's that omitted variable's relationship with X, the variable we included, but also with Y. So what do you think the covariance is between parental income and whether or not you work a job while in college? Higher parental income, do you think you're more or less likely to be working a job in college? Probably less likely. So we have a negative covariance. If we were to include this omitted variable parental income, what impacts, this is kind of a weird one, but what impacts do you think would that have, not controlling for anything else, would that have on your college GPA? If your parents have more income, growing up, what did you have more access to? Higher quality schools, right? Maybe not as dangerous of an area to live in, right? Where you could focus on school. So it's likely that parental income, it would have what impact or what predicted effect on college GPAs. So I've got a positive beta 2. The covariance between the omitted and included variable would be negative. So the sign of my bias should be negative, right? That's how we would kind of walk through a problem like this. So hopefully everybody gets this one correct, kind of showing you the answer and walking you through it here. We already talked about this one as well, but as I add in more variables, we said, what's that going to do? Is that going to penalize my adjusted R squared more or less? Part of the adjusted R squared is that it's penalizing us for including more variables. So in penalize, what is that going to do to our adjusted R squared? It's going to decrease it, right? Adjusted R squared, if we're penalizing something, right? We throw more variables in there, it's going to decrease that adjusted R squared even more. So if our adjusted R squared is getting even lower, right? Our actual R squared, we're just throwing more variables in there, what's going to happen to it? Definitely goes up. But our adjusted R squared, we just said, we're going to get over penalized, so it's going to get lower and lower. So that gap in between the R squared and the adjusted R squared should do what? The R squared stays the same. We said the adjusted R squared, it's getting penalized more and more, so it's getting closer and closer to 0. So that gap in between the two should be wider or is increasing. Right? So that's why the answer there would be kind of increase. And I'm probably over time now. Well, I'm right on time, right? So I changed the times to just, as long as you get that submitted before you leave today, you should be good. You get the full points. Other than that, please, please, please ask me for help as you're working on that problem set, and please, please, please start working on it early and not next Wednesday, okay? All right, have a fun, safe weekend. I will see you guys on Tuesday.